Yeah, sure. So yeah, as I said earlier, today we will be looking at the topic binary search, and this is the fifth week of Road to Competitive Programming series connected by Coach of Shastra chapter. And here I am Arjun in front of you to handle today's session. So now let's get started. So what in the first place, what is binary search and why is it this important? Let me start with a simple concept. So if I'm giving you an array that is a list of numbers, which is going to be something like 2, 4, okay, 2, 4, 5, 3, and 1. And I'm asking you to find the number 5 and return me its index. So what will you do? Obviously, the approach everyone will follow is going to be the linear search, which all we are used to, and it is going to be a very intuitive solution. So we start an iterator from the zeroth index. So let me write the indices. So we start from the zeroth index, check if this number is equal to our target. No. Then we move on to the next one. Here also we find that it is not equal to 5. And next we move on to the second index and we see that this is the number we are looking for. So in that case, we would be returning the answer 2, that is the index of the number 5, and then we will be breaking the for loop. But what if I've already given you that this array is going to be sorted? So if it is going to be 1, 2, 3, 4, and 5, is there going to be any advantage over this? So here let us take the case that I am asking you to find the index of the number 3. Do you have any advantage over this? Uh, by intuition, you can say that why not? Here also we can take the concept of linear search and easily find the index of number 3. But what if I say ask you to find the number? Let me take it as let me modify this array a little bit. So it is not going to be 3 over here. So it is going to be 4, 5, and 6. And now I am asking you to find the number 3. So you will start an index iterating from the first index. So let me go to the second one, third one, and nowhere you will be able to find 3. After going to the last number, that is 6, you would be satisfied that this array doesn't contain the number 3, and you would be returning something like a false or a -1 in this case. But when you reach this index, that is index 2, you would be sure that the number 4 is obviously going to be greater than number 3, and traversing this array beyond this is going to be a waste of time. And also, if you're going to have a sorted array, you can take the idea of this case that we have encountered now, that is beyond 4, it is waste of traversing. This is the idea behind binary search. So let me put it in simple words. Binary search is an optimized search technique that works better on sorted lists, and it works with the concept of divide and conquer. So now let's take an example test case and try to understand this even better. So let me take that the array is going to be something like 1, 2, 4, 6, and 8. So what do we do here? So here let me take the target to be something like 1. So the idea behind binary search is that in the first case, we would start dividing this array into two pieces at every stage, and then we would be optimized in an optimized way. We would be traversing the part only in which we would think that the target would be present. So now let's start the idea over here. So first I will be dividing this into two parts. So the first part will contain 1, 2, and 4. The second part is going to contain 6 and 8. So if you see over here, T1, T equals 1, and this cannot be present in this array because the smallest element in this array is going to be 6, and beyond 6, we would definitely not find the number 1. So we would eliminate this and go to the left side. And again, I'm going to split this into two parts. So here I am going to have 1, 2, and 4. Here also we can eliminate the right part 4 because the smallest in this array is going to be 4, and we see that the only element that is present in the right side is going to be 4, and we know that 1 is not going to be present in the right side. So the only part we are left with is 1 and 2, and we would now split it again, and we are going to follow the same idea, and finally we would be able to locate that 1 is over here. So what are we optimizing over here? If we are going to take the approach of linear search, we would have traversed 5 elements. But here, if you see, we had eliminated 1, 2, 3, and 4 elements over here, and we have only checked one element. So in each step, we are dividing the array into two parts, and then we are only looking at the side where we would be sure that the element might be present. And if the element is not going to be present, in that case, we would be returning -1 or false or whatever it is. It depends on the problem statement. So now let's see how the algorithm works. So if the array is going to contain 5 elements, we would be taking a low index to be 0 because array indexing starts from 0, and then a high index which is going to be at 4. That is, if the size of the array is going to be 5, we would be sure that the indices would be 0, 1, 2, 3, and 4. That's why we are taking the lower index to be 0 and higher index to be 4. And in each step, we would calculate the middle elements index, which is going to be low plus high divided by 2. But this is not going to be an efficient solution to calculate middle, because this would be troublesome when we come over overflows. Because if you take the, let me take low to be something like int max, and also high is going to be let me take it as int max minus something like 4, and high is going to be int max minus 2. So the array size is going to be around 2, and the lower index is going to be int max, and the higher index is going to be 2. And in this case, if you are going to calculate low plus high, this value would obviously give us an overflow case, so that the middle elements index would go wrong. So what do we do? A better approach to find the mid would be to take low plus high minus low divided by 2. We are taking the lower index and we are finding the difference between the higher index and the lower index, and we are just dividing this by 2. And here you will be obviously sure that high minus low will definitely not give you an overflow. So finally dividing it by 2, we are adding it with the lower index to find middle element. So now what do we do? So we have the middle element and we check if the array's middle element, that is, if the array is going to be named ARR of mid is equal to our given target. If yes, then we return mid, which is going to be the index of the target element. Otherwise, if the middle element is going to be greater than the target, for example, if you have 1, 2, 3, 4, and 5, we are looking for the number 2. First, our low would be over here, our high would be over here, and middle will be at 3. If I'm not wrong, the middle should be at 3, 0, 1, 2, 3, 4. And the middle will be 0 plus 4 minus 0 divided by 2. Yeah, so the middle element is over here. And now our required element is going to be, the target is going to be 2. Now we check this middle element with our target, but the middle element is greater than the target. So we are sure that our target will not be definitely present in the right side. So we eliminate this and we should be moving to the left side. So how do we do this? Simple. Now we make the higher element to be middle -1. So the new range will be only this, and we need to check only these two elements to search for the target. So what do we do? So if the ARR of mid is going to be greater than target, then we make the higher index to be middle -1. Otherwise, we would be sure that the middle element will be less than the target. In that case, we would make lower element equals middle +1. That is, we would eliminate the left side of the array and move on to the right side. So with this heat, we would go solve a lead code problem, which has been asked in many interviews, but I'm not sure if it's asked in many interviews. And this is going to be the classic binary search. So I hope you will get this approach when we start live coding. So what is the question? Given an array of integer nums, which is sorted in ascending order, and an integer target, write a function to search target in nums. If the target exists, then return its index, otherwise return 1. Your you must write an algorithm with O of n runtime complexity. We would discuss about this a little bit later, but what they're asking to do is just run binary search, and we should be finding the index of the target element. If the target element is not present in the array, in that case, we would be returning -1 answer. So what do we do first? So first, I would make int left equals 0. So here for better understanding, I am taking the low to be left and high to be right, and height would be equal to num's size, that is the array size -1. So this will give us the last index in the array nums. And I would be declaring a variable called middle. And now I would be running the while loop. So what is the condition for the while loop? So that we haven't discussed yet. So when do we terminate this loop and say that the target is not present? When the low becomes greater than high. Because if low is equal to high, in that case, it means that we have an array something like this. And if low and high are pointing to the same element, that means that we have only one element to be searched for. If low becomes greater than high, then we would have no point in searching the array, because there is no meaningless range in the array where we would be searching for the target element. So that is the termination case for the while loop. So yeah, so the condition is going to be low is less than or equal to high, that is the right. And what do we do here? First, we generate mid. So as I said, mid is going to be low plus high minus low divided by 2. Hope you are getting this. Now, if the nums of mid equals the target, in that case, we would be returning the middle element. That is, they've asked for the index. That is why we are returning mid. Otherwise, if nums of middle element is going to be greater than the target. So what do we do in this case? As we have already discussed, we would be searching in the left side of middle. So r equals middle -1. Else we would be sure that we should be searching on the right side, because the middle element is going to be less than target, and in this case L will equal middle +1. And if this for loop while loop is terminated without returning anything, then we should be sure that the target element is not present in the given array. So in that case, we would be returning -1. Are there any doubts with this approach? Is everyone comfortable, or let me reiterate again over the idea? Can somebody please confirm? Are there any doubts regarding this? So yeah, if you're feeling a little bit tough, I would be zooming this in a little bit. Yeah, okay. So I suppose there are no doubts. So let me move on. So let this run this code and try submitting. Yeah, it has compiled successfully. So yeah, this is the solution for the classic binary search problem. And the problems we are discussing today, we would be giving the links for the same in the CP resource sheet that we'll be providing after this meet. In that, if you feel good, you can go and you can submit the solution on your own, so that it will be a good practice. Also, we have included practice problems with the same idea. We are going to discuss the problems today. So let me move on to the next concept. So what is the time complexity of binary search? At each stage, we are dividing the given array into two. So the overall time complexity would be O of log n if the array size is going to be n. So when will this happen? The average case time complexity and also the worst case time complexity would be O of log n, because obviously we are eliminating half of the array at each stage, and finally when we find the array, we would have gone through almost log n iterations. So the worst case will occur when the element is not present in an array. So at any stage, we would not be able to terminate the while loop, returning some answer, and we should be going on till the low becomes greater than high. The average case will occur when you see that at some cases we would be returning the answer when we encounter the middle element earlier. So what are the best case and what is the best case time complexity? So it is going to be O of 1. It is constant time complexity. This will occur when the middle element of the first iteration is going to be equal to target. So then and there we would be returning the middle element and breaking the for while loop. So yeah, this will take O of 1 time complexity. So if you are not given a sorted array, in that case, you would take n log n to first sort the array, and then to run binary search, you would take log n time complexity. So in that case, the overall time complexity would be n log n. So I hope you get this perfectly. So now you might have a question in your mind. So binary search is a simple problem where we divide the array into two parts and then we search for some target element. So why is a very important concept in the field of competitive programming, as well as why are many questions asked in interviews. So binary search is not only for finding the element in the target, not only finding the target element in the given array, but there are also many other uses. Let us look at it one by one. So first, let me also state that there is a Stl function for binary search, which is going to be binary underscore search. So this is a function that will return a boolean value, and the parameters it is going to take are the iterator to the first index, that is the first starting iterator, that is going to be the start address, let me call it start address, and also the ending iterator, and the element to be searched for. Let me name it target. So this will return true if that element is found. Otherwise, this function would be returning false. So there are other famous questions based on binary search. Like for example, let me take the case again 1, 2, 3, 4, and 5. And I am saying that find the first number that is going to be greater than or equal to 2. Greater than or equal to 2. This is also a binary search question which is known as lower bound. Sorry. It is going to be lower bound, which says that we should be finding the first element that is not lesser than the given value. That in other words, it is greater than or equal to the given value. So how do we find this? So in the previous case, we were given a target, and in each case, we were checking if that middle element is going to be equal to the target or not. If yes, in that case, we would be returning the middle element. Otherwise, we would be keep on going until the low becomes greater than high. But here we have been given a condition where we should be finding the first element that is greater than or equal to 2. For example, if this array is going to be 1, 4, 5, 6, 8, in that case, we would be returning 4. Here, we would be returning the 2 as the answer. So in each case, the answer is differing. So how do we encounter this problem? For these kind of problems, a best way to do is based on marking the elements as true or false. So what do I mean by this? So we need the first element that is going to be greater than or equal to 2. And in this case, 1 is not going to be the first element which is greater than or equal to 2, so false. And rest of all elements are going to be true. So here I am arranging them in a false followed by true manner. So we can take this as a sorted array and then we can start finding the first true, which is going to give us the index of the first element, which is going to be greater than or equal to 2. So how do we do this? It is going to be very simple. As discussed in binary search, all the conditions would be same. So we would take a low element, we would take a high element, which is going to be right or high, however you can call it. And also we are going to find mid in the same way, which is going to be L plus R minus L divided by 2. And we are going to run a while loop with the condition that L less than or equal to R. But where is the difference? Here, we would not be very specific when we will be encountering an element. So for example, if low is going to be here and high is going to be here, and in the first iteration the mid will be over here, this element is greater than or equal to 2. But will this be the first element which is greater than or equal to 2? No. So that is where the problem comes. We cannot confirm by looking at some element that this is going to be the answer. So what do we do? Apart from these variables, we should also be maintaining a temporary variable called answer. And what do we do? Inside this while loop, we check if the current element, that is ARR of mid, is going to be greater than or equal to the target. If yes, then what is the next step we should be taking? We would be very sure that the first element is going to be towards the left of the current element. But this current element can also be a possible answer. So we first store this in the answer variable, and then we make r equals mid minus 1. That is, we would be traversing the left side of the array. Otherwise, what do we do? Simple. If this condition is not satisfied, we make L equals mid plus 1. So let me take an example and dry run this so that you would be understanding it better. So let us take the example to be 1, 2, 6, 8, 10, and 12. So the indices are going to be 0, 1, 2, 3, 4, and 5. So initially, left would be over here, and we will have the right over here, and the middle would be somewhere over here if I'm not wrong. Sorry, the middle element would be,
The middle element will be the index
yeah,
2.
yeah, I have gone wrong. So middle element would be here. So we first check if this element is greater than or equal to the target. So what, let's have the target equals 2 again. Yes, so the middle element is greater than the target. So our possible answer would be index 2, because we have an element which is going to be greater than or equal to our target. But we are not sure if this is going to be a possible answer. If this element is going to be greater than a target, we will be definitely sure that all the elements towards the right would be greater than the target, but we are not bothered about that. We need the first element which is greater than or equal to target. So definitely we would be traversing the left side of the array. That is why we are making r equals mid minus 1. So our r will go over here, and now we are left with only two elements, and our middle would be over here. Sorry, middle would be over here, same as L. So now let's see if the middle element is going to be greater than target. No. So now we need not change our answer. What we need to do is just make L equals middle plus 1. So our L and R will be pointing to the same element, and so does the middle one. So here we see 2 is greater than or equal to 2, and so that we change our answer to be 1 because 2 occurs at index 1. So after that, our our R would go middle minus 1. So now our R will be pointing to the 0th element, and as L is now greater than R, we would be terminating this while loop, and finally we will be returning the answer as 1. So I hope you get this. Are there any doubts regarding this? Fine. Thanks for confirming. So this is all about lower bound. So what if the element is not present in the array? That is, we are looking for the first true, but what if all are going to be false? In that case, simple, we would be returning minus 1 answer. So how do we encounter this case? Whenever we declare the array, element answer, we would be initializing it to be minus 1. So if there are no substitutions for answer, finally when we return answer, it would be minus 1, and that will say the online judge or the user who is going to implement the lower bound that the target is not present in the array. And same goes for upper bound. But the only difference over here is we would be required to find the first number that is going to be greater than the target. So the only difference we would be making in our algorithm is that when we check the middle element, what we do is we check if AR of mid is going to be greater than the target. If yes, then we would be storing the middle element in a temporary variable, and then we would be moving to the left. That is R equals mid minus 1. Otherwise, what we will do is we would be making L equals mid plus 1. So this is the only difference between lower bound and upper bound. You also have Stl functions which are lower underscore bound and upper underscore bound, which would perform the same functionality as our algorithm, but the only difference is that it would be returning an iterator toward that particular element. So if you want to find its index, you can use this lower bound or upper bound function, and finally you can subtract arr dot begin. So this is going to be the iterator to the first element in the array. So what are the parameters it is going to take? As usual, the starting iterator, ending one, and the target value. And same goes for upper bound 2. I hope that Sreesan has discussed this already in the STL session, which was the first or the second week of CP to road to CP. So I hope you are comfortable with these. So can we move to the next problem? Yeah, thanks for confirming. So now let's take a step ahead and let us move to a medium problem, which has been asked in many interviews. If I'm not wrong, it has also been asked in Amazon interviews. So what is the problem over here? So the problem is to find the minimum in a rotated sorted array. So let me read the problem statement. Suppose sorry, suppose an array of length n sorted in ascending order is rotated between 1 and n times. For example, the array nums is going to be initially 0, 1, 2, 4, 5, 6, 7, might become 4, 5, 6, 7, 0, 1, 2. That is, they are taking some cut in the array, and then they are swapping the initial and the final parts. That is, if you see over here, 0, 1, 2 has come after 4, 5, and 6, 7, which was initially before 4, 5, 6, 7. So they are taking some pivot point and rotating that array, and they have also said that the array is rotated between 1 and n times. So notice that rotating an array one time returns the array a of n minus 1, a of 0, a of 1, so on up to a of n minus 2. That is, the last element comes to the first. So if you are going to rotate it the second time, the second last element will be coming to the first position. Given the sorted array nums of unique elements, return the minimum element of this array. So yeah, this is our problem. Let us go to the whiteboard and start discussing the same. So what they're asking us to do, they have said that they would be giving us an array nums, which is going to be initially sorted in ascending order. And they've also said that it only contains unique elements. And they are rotating this array 1 to n times. So after rotating n times, you would be sure that the array would be same as the initial array. So now let us take an example and try to understand this problem better. So if the array is going to be 1, 2, 3, 4, and 5, let us suppose I am trying to find the minimum element in this array. So easily I would be able to say that the first element is going to be the minimum because they've already given that it is sorted in ascending order. But what if I rotate it two times? So after the first rotation, the array will become 5, 1, 2, 3, and 4. And after the second rotation, the array would become 4, 5, 1, 2, and 3. Now our task is to find the minimum element in this array. So how do we find this? As usual, the idea we have discussed is to arrange this array, that is to mark the array elements followed by a set of falses and trues or trues and false. So how do we do this? It is simple. The condition we are going to take is that the element we are encountering should be greater than the last element. So we have seen that it is rotated over here, and we should be having an array marked something like true, true, false, false, false. And here our aim is to find the first false, which is going to give us the minimum element. So how do we mark this in such a way? If you see, we have marked true to 4 and 5. So we see that 4 is greater than 3 and 5 is also greater than 3. So the condition over here should be ARR of mid should be greater than ARR dot back. You might also have a question in mind. Why I am taking this condition instead of taking ARR of mid is greater than or equal to the first element? Because 4 is greater than or equal to the first element, 5 is greater than or equal to first element, so these elements will have true, and all the rest of the elements are not greater than 4, greater than or equal to 4. In those cases we would have false. So this is also a possible case, right? So why are we not taking this condition? Because they have given that they can also sort the array n times. So after n times, it would be same as the initial array. And here if you see, you cannot mark it, all the elements would be greater than or equal to the first element in this case. And it is meaningless to say that we are looking for the first false, because there are no false there are no elements marked false in this array. So does this mean that minimum element does not exist? No, the minimum element exists, which is going to be 1. So that is why we are eliminating this case, and we are taking this as the criteria for our binary search algorithm. So now let us go code this in lead code, so that parallelly I can explain you how the algorithm works, and you will also be able to understand it better. So what do we do first? We take low, high, middle element, and also answer. So low is going to be initially 0, high is going to be nums dot size minus 1, as we discussed earlier, and also our answer would be, so minimum element will always exist, so we would not be required to initialize our answer with some variable. And now let's start our while loop. So while low is less than or equal to right, which is going to be our usual condition, we generate mid, which is going to be L plus R minus L whole divided by 2. And if nums of mid is going to be less than or equal to nums dot back, that is the last element. So sorry, we have taken the condition that it should be greater than the last element, right? So we would go by the same. So where are we encountering the middle element? The minimum element. It is going to be the first false. So if the condition is going to be greater than the last element, the first false will occur when it is less than the last element, less than or equal to the last element, because we have taken greater than over here. So our condition would be less than or equal to the last element, which is going to be ARR dot back. In that case, this might be a possible answer, so that we take answer equals mid, given sorted your array, okay, return the minimum element. They're asking the minimum element, not the index. So we would be returning nums of mid in this case. And also, this might be a possible answer, but a better answer might exist towards the left of mid. So we make mid minus 1. So otherwise, we would be definitely sure that the answer would lie in the right of the array, because over here, if you see, if we are encountering some true element, let us suppose that the true element we have encountered is going to be 4. we would be obviously sure that the first false would be occurring towards the right. That is why we are moving towards the right. So we make L equals mid minus 1. And after this while loop is terminated, we would be returning answer. So let us try running this code. So we have no compilation errors. And yeah, it has got accepted. So this is how you find the minimum element when an array is sorted 1 to n times. Even if it is sorted n times and the array is same as the initial array, that is, there is no change in the given array, even then this algorithm will be perfectly working. So I hope you get this. Can we move to the next problem? Are there any doubts with this one? Okay, Barney, she has no doubts. So shall I assume that there are no doubts for everyone? Yeah, so everyone is good to go. Fine. So the next problem we are going to encounter is going to be find the peak element. So a peak element is an element that is strictly greater than all its neighbors. Given an integer array nums, find the peak element and return its index. There are multiple peaks, return the index to any of the peaks. You may imagine that is nums of minus 1 and nums of n may be minus infinity. You must write an algorithm that runs in O of log n time. That is, they are asking you to somehow implement binary search to optimize this problem. So yeah, let us see how the problem goes. So they are giving a mountain array which is going to look something like this. So let me take the elements as 1, 2, 3, 4, 5 and 3, 2, 1. So this is somewhat how the array is going to look like. So it will be definitely contain a peak which is going to be greater than both of its neighbors. And they are asking what the peak element is going to be. And they have said that there can also be multiple peaks. But first, let us concentrate on one peak. So this whole array is not sorted, but a part of the array is sorted in ascending order and rest is sorted in descending order. So how do we implement binary search over this? Simple. As our initial strategy after looking at any problem and after deciding that it is going to be based on binary search, the first thing that you should be doing is to mark the elements in a set of trues followed by false or else false followed by trues. So how do we do this? So let us see. Let us write the array once again over here. 1, 2, 3, 4, 5, 3, 2, and 1. So the element which we are going to return is going to be 5. So we see that all these elements up to 5 are sorted in ascending order and rest of all are sorted in descending order. So we must be sure that every element in this part should be smaller than the next element. Let us take that as the case. So here we would be able to see that 1 is less than 2, 2 is less than 3, 3 is less than 4, 4 is less than 5, and we have 5 over here, which is not less than the next element. And this goes on for all the 3 elements. So these are falses. So it would be meaningful to say that we are looking for the first false in this array. So how do we do this? Simple. As usual, we would be taking our variables which are going to be low, high, and mid. We would be also requiring a temporary variable. And let me come to the edge case after going through the algorithm. So what do we do? As usual, the for while loop is going to be L less than or equal to R. And here we are looking for the first false. So for every element, we generate mid, which is equal to L plus R minus L whole divided by 2. And we check if the middle element, that is going to be ARR of mid, is going to have is going to be greater than the next element, mid plus 1. So we see that we are looking for first false, and the condition for it should be greater than the next element. And they have also given in the problem statement that the peak would be in such a way that that element is strictly greater than its neighbors. So there is no way of having what you called equal elements and calling them as peaks. That is not possible. If we are going to call some element as peak, it would be definitely strictly greater than both its neighbors. So if this element is going to be greater than the next element, then it can be a possible peak. But are we sure that this is going to be the peak? No, because even for 2, we would be having this case to be true. Because 2 is greater than the next element. But we cannot call 2 as the peak element because 2 is less than 3. But we need the peak element to be greater than both its neighbors. So L can be a possible answer. And where do we look for a better answer? Towards the left or towards the right? If we are having falses as our target and we are looking for the first false, then obviously we are moving towards the left. So in this case, the condition to be moving forward is going to be r equals mid minus 1. If this case is not going to be true, then we have the else over here, which is going to take L equals mid plus 1. So what does this mean? So this means that we have encountered some element which is marked as true, but we are looking for false. So we should be moving towards the right. And that is why we are making L equals mid plus 1. So what is the corner case over here? Let us take the case 1, 2, 3, 4, and 5. And what is the peak element? It is going to be 5 because they have said to assume the first element to be minus infinity and also the last element to be minus infinity. So the first false will occur over here. So all these would be true and this would be false, and this is called the peak element. But if we are going to take L equals 0 and R equals the last index, how do we check if this element is going to be greater than mid plus 1? Because there is no index existing in the array as mid plus 1. So that will not be possible, right? So in that case, what do we do is, initially, we would be having our answer to be the last element, that is pointing to arr dot back, and we would be having our low and high in the first and the second last position respectively. So r would be n minus 2 and L would be at 0. And we would be checking for peak element only over here. If there is no peak element over here, then they would be definitely sure that this last element is going to be the peak element. So answer would not be modified, and finally we would be returning answer. I hope you get it. But what if there are going to be multiple peaks? So let us take a case with multiple peaks and check if our algorithm works. So if you see, this array is increasing like this and again going down over here. And here if you see, there is another peak which is going to be 5 and again it is coming to 1. So you would be able to see that there are 2 peaks. So let me mark the trues and false. So 1 is going to be true because it is less than 2, and 2 is going to be 2 because less than 3, and so on. But 4 will be a false, and then we have false, false, sorry, this would be true, it is going to be false, and this is going to be false. So here we are looking for the first false, but in between we are encountering some truths. So how do we manage this? It is simple. If we take L over here and R over here, and we would be going somewhere over here, which is going to be the middle element. Yes, here will be our middle. So the middle element is going to be false and looking for the first false. So we traverse towards the left and we would be sure that there are no false towards the left. And finally, we would be returning F this 4 as our answer. So we are sure that our algorithm would be definitely returning some peak. We cannot be sure which for peak it is going to return. But since the problem is asking for the index of any of the peak, we need not make any changes to our algorithm and this would work perfectly. So let us start coding. So L is going to be equal to 0, int R, which is going to be the high, is going to be nums dot size minus 2. This is where people might go wrong because at each case we are checking the next element also. So we should not go beyond the array size. So that is why I am taking r equals nums dot size minus 2. And what will be the answer? So the answer would be initially nums dot size minus 1. So the answer is initially pointing to the last element. So if we don't get any peak, then in that case it will mean that the last element is going to be the peak. So while L is less than or equal to R, we generate mid as usual, L plus R minus L divided by 2. So the condition is going to be if nums of mid is going to be greater than nums of mid plus 1. So this is a false case. So if we are encoding a false case, what should we do? We are looking for the first false. So we mark this as a possible answer and then we are moving towards left. So r equals mid minus 1. If this is not the case, we would be sure that we have encountered some element which is marked as true and we would be moving to the right. And finally, we would be returning answer. And I hope this should run perfectly. So yeah, it has compiled successfully. And now let's try submitting it. And yeah, this has successfully got accepted. So this is the solution for finding the peak element, which is going to run in O of log n time, because we are using binary search as the elements are going to be sorted in some way. At least a part of the array is going to be sorted and the next part is going to be sorted in a different manner. That is, if the starting is going to be sorted in ascending order, rest is going to be sorted in descending order. So that is why we have got the intuition to use binary search in this, and we have successfully marked the elements as trues and false so that we got a perfect algorithm to find the index of any peaks. So I hope you get this. Shall we move to the next problem? So we have two more problems to be discussed. One is going to be of the difficulty medium, and the final one is going to be of difficulty hard. So yeah, I think we are good to go. So let me close this. And the next problem is a matrix based problem. So what is the question? The question goes by the name search in the 2D matrix 2. So that is a type 1 of this problem, which is going to be just search in a 2D matrix. And I have given you that as a practice problem. And after the session is over, you can try that problem on your own. And if there are any doubts, you can post it in our Discord server. So link to the same will be provided in the resource sheet, which we will be providing you after the session gets over. So what is the question? Write an efficient algorithm that searches for target value. Sorry, it is going to target value in a matrix of size m cross n, and there's going to be integer matrix, and they have given the matrix has some properties. So what are they? Integers in each row are sorted in ascending order from the left to right, and integers in each column are sorted in ascending order from top to bottom. So this is going to be an example matrix. Let me take a screenshot of this and let us move to the whiteboard. So this is how some matrix given to us will be looking like. So let me mark the indices first. So this is going to be 0, 1, 2, 3, 4, and again 0, 1, 2, 3, and 4. And here the target element is going to be 5, as they have marked green over here. So they have given that all the rows are sorted in ascending order from left to right, and all columns are sorted in ascending order from top to the bottom. So how would this help in finding the target element? Does anybody have an idea? As we've already discussed 2 to 3 medium problems on binary search, you are free to open up and say if you get some idea based on this problem. Yeah, someone can unmute yourself and just try it out. We are all learning, guys, so if it
Yeah,
goes
it's
wrong,
okay if it goes wrong. You can just try.
is there someone who's willing to try? Okay, so let me get into the solution. So, what are we looking for? We are looking for some target element in this matrix where we are given the conditions that all the row columns are sorted in top to bottom fashion and all the rows are going to be sorted in left to right fashion and in ascending order to be specific. So we are looking for 5. So how do we find it? So the algorithm is going to be something like this. So if you split this array into 5 parts and you just look at each column, you would be sure that this first element in that column is going to be the smallest value. Am I right? So for example, if you are at some column 3, by looking at the first number in that column, you can decide if 5 can exist in this column or not. If the first number is itself going to be greater than 5, then we would be definitely sure that 5 will not exist in this column. So how do we make use of this? Simple. We would be having an iterator pointing towards the last column and the first row. So let me call it as row and let me call this as column. So now, first we would be deciding in which column the number can occur. So, which is the first column from right in which the number can occur. If we have decided the column, then we proceed row wise and try to find the target element. So in which way it is going to be binary search? Yes, we are first splitting this what you call the matrix in a column wise manner. So we are splitting it by each column and we are first deciding in which column it is going to occur. And if we are sure that in some column it is not going to occur, that is the first number in that column is going to be itself greater than a target element. And in that case, we are eliminating the whole column. So we are reducing the problem size, and at each stage we are getting a smaller problem in which a smaller matrix in which we are looking for the target element. So this is some form of binary search. So let me get into the algorithm. So first we are at column number 4 and row number 0, and the element we are looking at is going to be 15. So 15 is the first element in column number 4 and it's itself greater than 5, which is going to be our target element. So we are definitely sure that 5 will not be existing in this column. So we rule this out. And what do? We move to the next column from right. So here the first number is going to be 11 and 11 is also greater than 5. So we would be eliminating this whole column and moving to the next one. Here also if you see the first number is itself greater than 5. So we rule out this whole column and we move out to the next column. And here if you see the first number is less than 5. So there is a possibility that 5 can exist in this. So we next fix this column and if we see the current element is going to be equal to the target. If not, we increment R. And here we see that it is going to be 5 and yes, we have encountered the target, and in that case what we'll be doing, we would be returning the index of that. So what are they asking for? Write an efficient algorithm that searches for the target value and they are outputting true. So they are just looking for a boolean value. They are just asking if that element is present or not. So I hope there are no doubts. But there can also be another case. Here we have easily found out the target, but there can be cases where the target is not easily found. So let me change some values in this matrix. So let me take this one to be 3 and this element to be something like 6. So yeah, so let me write it over here. So this element is going to be 6 and this is going to be 3. Still we haven't disturbed the properties because this row is sorted and these two columns are sorted. So now let's try the same algorithm. And now what will we be doing? We would be taking the column to be here and the row to be here.
Sorry to interrupt. Is
Yeah.
the first row sorted?
Oh,
Yeah,
I
1,
have
4,
made.
and 3.
Yeah, it's my bad. I will change it out. So what do we do over here? So let me change this number to, let me have it as 2 over here. Now is it fine?
Yeah, I guess it's fine now.
Yeah, okay, fine. Thank you for mentioning that. So the column is going to be over here and row is going to be over here initially. And we see that 15 is greater than 5. So we rule out this column, move on to the next one. And we see that 6 is greater than 5. So rule out this whole column, move to the next. And now we see that 3 is less than 5. So this is a possible column where 5 can exist. So now we see that if the current element is equal to target, no, a current element is going to be 3, which is not equal to target. So now we increment R and we do not disturb C. So now we see that the next element we have encountered is going to be 8. Is 8 equal to 5? No, obviously it's not. So you might think that we would be incrementing R and moving to the next element. That is where we'll be going wrong. So we would be checking if this element is going to be greater than target. In that case, we would be definitely sure that all the elements below this element will be definitely greater than the target, and there is no point in searching this. So now we are instead of eliminating the whole column, we have eliminated the last four values, because by first looking at 3, we got an intuition that 5 can exist in this column, but the second element is going to be 8. So we are sure that 5 cannot exist in this column. So in this case, what do we do? Same as we did for the first row. If we are going to encounter some number which is going to be greater than the target, we just move to the next column. So are you getting it? So am I connected? Yeah. So we move to the next one and we would be checking if this element is going to be target, and here yes, so that we would be returning true in this case. This is how our algorithm is going to work. So you might have a doubt that after moving to the next column, why do we don't start from the first element? So we have moved to the next column and we directly started looking for the second element. Why didn't we check the first element? That is because in this column we saw that 3 is going to be a number less than 5. And if 3 is going to be a number less than 5, obviously all the numbers in that first row towards the left of 3 would be less than 5. So there is no point in checking the first elements after this point. So that is why when we encountered 8, we just shifted the column, but we did not shift the row. We stayed in the same row and we checked if the current number is going to be equal to target or not. So I hope you will get this algorithm even better when we start coding, because this might look this might sound a little bit confusing, because on the first day when we have looked at the binary search algorithm, we have started solving medium level problems. So for some it might look confusing, but do not lose the motivation. Keep practicing, and binary search is a very interesting topic. There are tons of problems on Lead Code and Geeks for Geeks. You can take them and practice one by one. And if there are any doubts, as I said earlier, you can always post it on our Discord doubts channel, and there will be always someone to help you out. So what do we do over here? as I said, first our column is going to be matrix of 0 dot size minus 1. So why did I do this? So I want the C to be initially over here, and I'm considering this as a vector which is going to be matrix of 0, and this dot size minus 1 will give me the last index of this row. So that is why I have taken matrix of 0 dot size minus 1, and as usual our row is going to be 0. There are no changes to be made. So while C is greater than or equal to 0 and row is less than the matrix dot size, because we are always going to decrement the column and increment the row, so we always need to check if C is greater than or equal to 0 and R is in the bounds of the matrix size. So if this is going to be fine, then our current element, that is, before these in all the problems we were taking the element to be middle, but here it is not meaningful to take the element as middle, so we take it as current element. It is going to be matrix of row comma column. And if current element is going to be equal to the target, in that case we return true. Else, if the current element is going to be greater than target. So what did we do over here? If the current element is going to be greater than target, we shift the column towards the left. So we do C minus minus. Else we were sure that the current element is smaller than the target, so that we increment the row. It's going to be R plus plus. And finally, if this while loop is not going to return any answer in any of the iterations, then we are sure that the answer is going to be false. That is, the target element is not present in this matrix. So let us try compiling this. It has successfully passed the sample test case, and now let's submit this. And yeah, we have got a correct solution, that is a success message. So let me reiterate on the solution. Initially, we are going to be at the last column, and we are looking to eliminate some rows and some columns, so that we would be making the matrix size smaller at each case. So first we be in the last column and the first row, and we check if the current element is going to be greater than the target, so that we can eliminate all the elements below it. So first for 5 we are eliminating 15, this row number 5, which is going to have the smallest element as 15. So 5 cannot definitely exist in this column. Next we move to this column where we will be having the smallest element as 11. So definitely no. We move to the next one, the smallest element is 7. So definitely no again. And we move to this column where we have an intuition that 5 can be present in this column. So we keep incrementing the rows until we find 5. And we have also discussed a case where the 5 is not present in the row which we found to be a good column. The 5 was not present in a column which we initially found to be a good column to be searched for the target, because the first element was 3. So we tried searching, but we encountered an 8, so that we eliminated all the elements below it and moved to the left column, but we did not disturb row. And I have also given the reason for the same. So is it fine? Did you understand this problem? Because this is a very important problem, and the frequency of this problem coming in interviews has been really high in the past few years.
I have a doubt, Arjun.
Yeah.
So can you show me the matrix?
Yeah, sure.
So you're starting at 15. So if 15 is greater than 5, you go one left, right? So to 11.
Yeah.
Instead of doing that, you can take the first row as an array, and then you can find upper bound to that, right? Upper bound to 5 is going to be 7. So that will give us O of log n, right? If in this case you're decrementing the iterator pointing to the column one by one, right? So that's linear time complexity.
Okay, so you are telling me that you can take the first row
and then find the upper bound for 5, which will be 7.
Yeah, 7.
And then you can also take that 7, 8, 9, 14, that column, and then you can do another one binary search in that column, right? So if you do not find that, then you can go for this next second next column and then a third next column to that.
Yeah, that is also a possible solution. I really like that. I did not come up with that when I looked at the problem. So in this case, what we'll be doing, we will be finding the upper bound, which is going to be 6 over here. So let me erase it and point it out neatly so that you will be able to understand. So here what we'll be having, so here I had marked as 2, 3 and 6. So you say that the upper bound will be here so that the
And
mm,
then in that column, you can do a binary search.
okay, I do a binary search over here.
You do not find, so you go to the next column.
Yeah, but
The way
when
you choose the column itself is going to be in time complexity of log n in this case, right? Instead of doing it in a linear time, if you decrement the column iterated by
yeah, yeah,
one,
okay, fine. If you find the upper bound and you end up in this column, how are you going to search 5 in this column?
I mean, you can do a binary search, right?
The smallest element which is going to be equal to 5.
Yeah.
So that will take a log n and again. But we can eliminate this column initially. But if you are going to do a binary search, you are definitely going to take log n because 5 is not present in this array. That will be the worst case for binary search when the target element is not present in that column.
Uh, you take upper bound to be 6, right? So you start from the first column that is next to this column. Can you do that?
Yeah, so we start from 3. Instead of
Yeah.
starting from 6, we will be
Yeah,
starting from
because 6
3.
is already greater than 5, so you don't have to search that column.
Yeah, this one way good, but what your algorithm does is to find the column, it is taking log n time.
Yeah.
But to search in that column, it is again taking a log n time.
Okay.
But what we can do instead is, as you said, we can use this to find the columns. But as I said, you can just increment the rows to find the number because when we encounter 3 and go to 8, we can then and thereby eliminate this whole row, telling that 5 will not be present in this, right?
Okay, yeah, fine, I understand.
Yeah. As recent said, this can also be a possible approach. I did not come up with that. So that will obviously reduce our time complexity. And even this is not going to be a very bad optimization. This is going to run. I have seen that my solution has run around faster than around 97% of the solutions on LeetCode. But I will definitely try recent solution too. And if you're really interested, you can also try the same. So, with that, I think we have come to the last problem of today's session, which is going to be median of two sorted arrays. This problem is a hard problem on lead code, and that means that this is a really hard problem. So, can we proceed with the same? Are you clear with all the concepts we discussed earlier? Only then you would be able to get the gist of this problem. Because all the problems we discussed earlier are going to be of easy and medium type, but this is a really hard one. Yeah, okay, fine. Thank you for confirming. So what they have given is, given two sorted arrays nums1 and nums2 of size m and n respectively, return the median of two sorted arrays. And the overall time complexity should be O of log of m plus n. So let us look at a sample test case and try to understand the problem better. So nums1 here is going to contain two elements, which is going to be 1 and 3, and nums2 is going to contain 2. And they have given that both the arrays are going to be sorted. So after merging them, we would be getting the array to be 1, 2, and 3. And in this new array, we are required to find the median. And they have said that the time complexity should be O of log of m plus n. So how do we do this? That is, for example, if the array is going to be something like 1, 3, 5, and 12, and here we are going to have 2, 4, and 10. These are the two arrays given to us, and we are sure that both the arrays are going to be sorted in ascending order. And after merging these two arrays, we would be getting 1, 2, 3, 4, 5, 10, and 12. And in this array, we are required to find the median. So as this is going to have odd number of values, the median here would be 4. For example, if it had an element called 11 over here, the median would have been 4 plus 5 divided by 2. In that case, you will be returning 4.5 as the answer. So I hope you get this. So how do we do this? The naive approach would be to take two pointers, that is one pointing to the first array and other pointing to the second array. So we iterate over them, and as they're already sorted, it would not be a big task for us to merge them in sorted order. We can do that in O of n complexity. So this array size is going to be m and this is going to be n. In overall, we will be getting O of m plus n time complexity to sort the array. And finally, we will be adding the two middle elements and returning the answer. Sorry, the two median elements and returning the average of them. And if the array size is going to be of an odd number, we will be just returning the median element. So, but they are asking us to optimize this, and we should be able to get a time complexity of O of log of m plus n. So, some way we should be able to apply binary search on this. So, how do we do that? So, let us take the same example and try to find out. So, the example we have already taken is going to be 1, 3, 5, 10, which is going to be nums1. And nums2 is going to be 2, 4, 6, and 12. What have we taken over here? Okay, we had taken 12 over here, and it is not going to matter much. Let us take this as the case. And how are we going to find the median of these two sorted arrays? So let me also write the combined array, which is going to be 1, 2, 3, 4, 5, 6, 10, and 12. And the actual answer is going to be over here. So these two numbers are going to give us the medians. So how are we going to do this? So the first observation we would be making is the left part of this array consists of left parts of these two arrays because they are sorted in ascending order, and also this array is going to be sorted in ascending order. So the minimum elements from these two arrays, that is these 1, 3, 2, and 4, would be forming the left part, and the remaining elements would be forming the right part. So this is the first observation we are going to make. And the next observation is going to be that there are no next observations. So let us get straight into the algorithm. Sorry for me blabbering over here. So next, what are we going to do? Let us take all possible cases for the splits to happen over here, and let us see what we can observe over there. So we are sure that the final array would contain 8 elements because nums1 is going to have 4, nums2 is going to have 4 elements. So the final array would have 8 elements, and the split is going to be obviously at between first 4 elements and the last 4 elements. So how are we going to do the split? So one possible case is to take 1, 3, 5, and 10 over here, and we would have 2, 4, 6, and 12. So nums1 is going to form the left part, and nums2 is going to form the right part. So let us have this as infinity. That is, let us suppose the last element of nums1 is going to be infinity, and the first element of this is going to be minus infinity. So this is one possible split. And the next possible one will be to have 1, 3, 5, and 10 over the second part. And as we have 3 elements over here, we should be taking one element from nums2 so that there are 4 elements in the left. So we take 2 over here, and we will have 4, 6, and 12 towards the right. And next possible split would look like this. We would have 1, 3, and 5, 10 are over here, and 2, 4 will be here, and 6, 12 are going to be on the right side. And next possible one would be 1 over here, 3, 5, 10 over the right side, and 2, 4, 6 over the left side, and 12 over the right side. And the last possible split is that 2, 4, 6, 12 will be forming the left part, and 1, 3, 5, 10 would be forming the right part. And here we have minus infinity, and here we have plus infinity. So these are the five possible splits we would be able to form. So now, how do we find which is going to be the best one to find the median element? So we see that this first row of each case we have taken is going to have elements from only nums1, and the second row is going to contain elements from only nums2. So we know that they're already sorted in ascending order, and so same goes for nums1 too. So we would be sure that this element would be lesser than this element. That is, in all cases, we see that the last element of nums1 on the left would be lesser than the first element of nums1 towards the right. Same goes for nums2 also. So this is going to be an obvious case, and we need not bother about them. But as we discussed earlier, the left part of the array is going to have elements which are going to be lesser than all the elements in the right, because we know that the final array is also going to be sorted in ascending order. So we cannot have some element in the left which is going to be greater than right. So what do we check over here? The condition we are going to check is the last element of nums1 in the left should be lesser than the first element of nums2 over the right. And in a similar manner, the last element of nums2 on the left should be lesser than the first element of nums1 on the right. So let me mark this as L1, L2, and this is going to be R1 and R2. The case we are checking is if L1 is lesser than R2 and L2 is lesser than R1. So let me check if there are going to be duplicate elements. So yeah, there can be duplicate elements. They have not mentioned about the same. So it is better to take L1 lesser than or equal to R2 and L2 lesser than or equal to R1. Is everyone able to understand this case? If yes, we can proceed further. After this, the problem is going to be very easy. Is everyone able to understand this? That is, L1 is going to be lesser than R2 and L2 is going to be less than equal to R1. Yeah, okay, fine. So next our problem has become very easier. So for each split, we checked if L1 is going to be lesser than R2 or not. Otherwise, we eliminate that. Let us go from here. Here we see that 10 is not less than 2. So obviously this is eliminated. Here 2 is less than 10, but 5 is not less than 4. So this is also eliminated. So next, if we see over here, 1 is going to be less than 12, but 6 is not less than 3. So case number 4 is also eliminated. So yes, minus infinity is less than infinity, but 12 is not less than 1. So 5 also eliminated. So the only possible case is going to be this, where 3 is also less than or equal to 6, 4 is also less than or equal to 5. So this is the possible split we would be having. So we would be having 1, 2, 3, 4 towards the left and 5, 6, 10, 12 towards the right of the array. So now, how do we find the median? So we see that all the elements towards the left are going to be in sorted order. Same goes for right also. So the maximum of this is going to occur in the last position of the left array. So if we sort them and arrange them, we will see that it is going to be 1, 2, 3, 4, and this is going to be 5, 6, 10, and 12. And these are the median elements. So what is this? This is going to be the maximum of left side, and 5 is going to be the minimum of right side. So should we check all elements and find which is the minimum? No. We need to just compare these two elements, R1 and R2, and similarly we need to compare L1 and L2. And the minimum of, let me write it over here, minimum of L1 plus L2 and the maximum of, sorry, it's going to be maximum of L1 comma L2 and the minimum of R1 comma R2 whole divided by 2, which is going to give us the median. Otherwise, we can have, if we are going to have odd number of elements, obviously some element is going to be the median, and we can always have it as L2 or the maximum of the left side alone. We can always have the median towards the left side, and we will be need to return only one element instead of finding the average between two elements. So how do we do this? As usual, we are going to solve this using binary search, as we already know. So we are going to first take the size of the two arrays. Let size of nums1 be 1 a, and let the size of nums2 be 2 a b. And then what do? We make L equals 0 and R equals A, because we need to run only binary search on one array. Because if we are going to have four elements in the first array in the left side, we are definitely sure that we are going to take zero elements from the right side. And also, if we are going to take three elements, we are sure that we are going to take only one element from the right side. So if the number of elements we are going to take from nums1 is decided, we would be definitely able to calculate the number of elements to be taken from nums2. So we always run binary search on only one of the arrays. And as usual, our while loop will have the case as L less than or equal to R, and then we would be making cuts. So what is a cut? As we see, this is going to be a cut. So if we are going to have 1 3 5 10 and 2 4 6 and 12, we would be starting the cut from middle, and then we would be checking if it is better to go right or to go left, as usual in binary search. But if we make the cut over here, what will be the index of the same? So let me put the indices of the numbers. So it's going to be 1 0 1 2 and 3. And if we are going to cut at the middle, it is going to mean that we are going to cut at index 1. So this element would be same as the position of the cut, and this element would be at a position the cut plus 1. Otherwise, what we can do is we can take b r equals the size of a itself instead of taking size of a minus 1 as we do in the earlier problems, so that the cut will happen at index 2 instead of index 1. So the very next element towards the left of the cut would be at index 1, and the next element would be same as the index of cut. Whichever is comfortable to you, you can go with the same. So what do we do next? So we find the index of the cut. So what is the index of the cut going to be? It is going to be L plus R minus L whole divided by 2. As we have discussed earlier, this is the general way in which we are going to generate middle element. But here instead of mid, we are going to call it as cut 1. And if cut 1 is this, what would be cut 2? So if we are going to cut at some position, that is if the element is going to have 0, 1, 2, 3, that is it is going to have four elements. In that case, our L will be equal to 0 and R will be equal to 4, and our cut 1 would be generated at 2. So we are going to cut somewhere over here. So that means that we have selected two elements from the first array. And how much elements do we need to select from the second array? It's simple. We just add their sizes plus 1 whole divided by 2. And this is the number of elements we need to select from the second array. So if we minus cut 1, this will finally give the number of elements to be selected from the second array. Let me also dry run on this. As the case we have taken is going to be 1 3 5 10 2 4 6 12. Initially our left would be over here, which is at the index 0, and right would be over here, which is at index 4. So our cut would be generated somewhere over here. So we have selected two elements from the left. So how many elements do we select from the right? So it is going to be a plus b, which is going to give us 4 plus 4, 8 divided by 2. We can also take 8 plus 1 divided, that is why we have added 1, because if the number of elements is going to be odd, in that case we would be required to add 1 to be able to specifically find how many elements we are going to select from the second array. So we take 8 plus 1. This is obviously going to be an integer division. So if we divide 8 plus 2 or 8 plus 1 divided by 2, it is definitely going to give us an answer 4. but this would be really helpful when the number of elements are going to be odd. So in total, we need to select 4 elements for the left part of the array. So we have already selected 2 from the left. We subtract it and we get the index for cut in the right element, that is second array. So the second array, the cut is going to be the index 2. That is, we are going to select 2 elements from the second array also. So that the left part of the final array will contain 4 elements and right part will obviously contain the rest 4 elements. So I hope you're able to getting it. Is it fine? Should I reiterate over the idea once again? So yeah, I hope everyone is able to get it. So let us see how right is generated. So as I've already said, it is going to be a plus b plus 1 divided by 2 minus cut 1. And I take L variables like L1, L2, R1 and R2. And if cut 1 is going to be initially at 0, then we have taken the left element to be minus infinity, and if it is going to be beyond the array size, we have taken it to be infinity. So we need to handle these cases now. So instead of discussing the algorithm over here, I think it is better to straightly start coding, in which side by side after writing each line, I would be explaining what each line means so that you would be able to get it easier. And also we are running out of time. So let me start it. As we already discussed, let us take int a equals nums of 1 dot size, int b equals nums of 2 dot size, and they have asked us in a time complexity of O of log of m plus n. But we are going beyond this, and we are making a further optimization that it is going to be in a time complexity of O of log of minimum of n plus n, because they have taken the consideration to be binary search running on both the arrays. But here we can first decide which array is smaller and we can run the binary search on that. So what do we do? If a is less than b, fine. We are going to run binary search on nums1. Otherwise, if b is going to be less than a, it would be obviously better to run the binary search on nums2. So what do? We return find median of sorted arrays. We are going to call the function again, but we are going to swap both the arrays. So we pass nums2 first and then nums1. So that the time complexity would be O of log of minimum of m plus n. What are we doing here? We are just checking which array size is smaller, and we are optimizing our solution based on this idea that the binary search will be only required to be run on the smaller array. So now let us take low to be 0 and right to be a, which is going to be size of nums1. And as usual, while L is less than or equal to R, I'm going to name a variable called cut. It is going to be something like the middle element. It is nothing different from the middle element, which is going to be L plus R minus L whole divided by 2. And cut 2 is going to be, so I made a spelling mistake over here. It's cut 1. And cut 2 is going to be a plus b plus 1 divided by 2. So we find the number of elements required for the left part of the final array, and then we subtract cut 1 from this to be able to select the remaining elements from nums2. So we are done. So now we need variables L1, L2, R1 and R2 so that we can check the conditions that L1 is always lesser than or equal to R2 and L2 is always lesser than or equal to R1. But before that, as I've already said, if the cut is going to be before the array, that is at index 0, or at the last, that is if it is going to be equal to a or b, in that case we would be taking R1, R2, L1, L2 be minus infinity or plus infinity accordingly. So now let us handle those cases. So L1 equals, if the cut 1 is going to be at index 0, that is before the first element. So we are going to take minus infinity in that case to be L1's value is going to be int min. Otherwise, we are sure that there will be always some element towards the left. So it is going to be nums1 of cut1 minus 1. Same goes for L2 also. So L2 is going to be equal to, if cut2 is going to be equal to 0, I'm making use of the ternary operator here, which is very easier to use rather than using if else. If you are comfortable with if else, you can also use the same. The only change you will be required to make is you should be adding the case that if cut1 equals 0, L1 will be equal to int min, else L1 will be equal to nums1 of cut1 minus 1. So here also it is going to be int min. Otherwise it is going to be nums2 of cut2 minus 1. So let me copy the same, and it will be easier for me to handle the cases for R1, R2 also. So it is going to be R1 and R2 over here. So if the cut1 is going to be at A, that is beyond the size of nums1, in that case we would be taking plus infinity as R1, which is going, otherwise if it is not equal to A, in that case it is definitely going to be equal to cut1. And the same goes for cut2 too. If it is going to be B, it is going to be R2 is going to be int max. Otherwise, R2 is going to be equal to nums of cut2. So we have handled these cases. Now let us come to checking the main condition, which is going to be L1 should be lesser than or equal to R2, and L2 should be lesser than or equal to R1. So if the case is satisfied and we go inside this block, we should be checking if the total array size is going to be odd or even. So how do we do that? We just add A plus B, and if it is going to be giving us a remainder of 0 when divided by 2, then we are sure that it is going to be an array of size even. So in that case, we will be returning maximum of L1 comma L2. As you saw over here, as you saw over here, we took the maximum of these two, minimum of these two, we sum them up and finally divided by 2, so that we will be getting the minimum element, sorry, median element. That is what we are going to be doing over here also. So it is going to be maximum of L1, L2, and then minimum of R1 comma R2, and finally we would be dividing this by 2. But as they are asking us for a decimal value, we should typecast this to a double, because the return type is also a double over here. So that it is better to typecast this to, so that whole answer would be typecasted to double. And I think I'm good to go. So what is the next case? So next case would be else over here. That is if the array size is going to be odd. In that case, we would be returning max of L1 comma L2. Sorry, we take these two elements and we max them and then return the maximum of them. So that is the element which is going to be just before the cut. So this is going to be the median element. So the final case would be, I'm making a mistake over here. So this else block should be for this if. So if this case is not going to be satisfied, so what do we check next? In the next case, we check if L1 is going to be greater than L2. What do we do in that case? L1 should be greater than R2. Sorry. What do we do? So we see that this first element is going, the last element we have taken from nums1 towards the left is going to be greater than the first element we have taken from nums2 in the right. If this is going to be the case, now we take one element from nums2 which is on the right side, and we take this element which is going to be from nums2 towards the left side. So when will this case happen? Let me take some case where this is occurring. Yeah, we are seeing over here that 5 is greater than 4. So this should not be the case. So we swap 5 over here and then bring 4 over here. I have mistakenly said wrongly. We are taking this element towards the right and we are taking this element towards the left. Let me write it over here neatly. So the case was 1, 3, 5. On the right, we will be taking 10. And here we have been taking 2 and 4, 6, 12 were over here. So if L1 is going to be greater than R2, then what we will be doing, we will be taking this element towards the right. As we have been taking this element towards the right, we would be required to add one element towards the left, and that element will be added from nums2 of right. So how do we do this? If this is going to be the case, we make r equals cut 1 minus 1. So what does this mean? So we are bringing the cut towards left. So if it is going to be like 1, 3, 5, 10, and we were having 2, 4, 6, and 12. So here initially the cut was over here, and for second array the cut was over here. So we are bringing this cut one step towards the left. So if we bring this cut one step towards the right, that will definitely mean that the cut 2 will go one step towards the right. So now we will have 1, 3, 2, 4 over here and 5, 6, 10, 12 on the right side. So that is what we are doing. R equals cut 1 minus 1. Otherwise, what we'll be doing? We would make L equals cut 1 plus 1. We are taking the cut one step towards the right. And finally, if this loop is terminated and we have not got the median, that will not be the case. But for safety purpose, I would be returning 0 in this case. As it is double, I will just typecast this and then return this value. But any array will definitely have a median, even if the array is going to be of size 1. That is, if there is only one element in the array, then even then the array is going to contain a median. So there will be no case for returning 0. So let us try running this code. So there is a typecast, or sorry, there's a compilation error. Okay, use of undeclared identifier, find median of sorted array. So I made a typo somewhere. Okay, it is going to be median of sorted arrays, and I've typed sorted array. That is the mistake over here. Now it should be running fine. Again, a runtime error. So what is it? Addition of unsigned offset overflowed. So let me just try to fix that. Let me reiterate over the code once again. So kindly bear with me, guys. So we are just swapping them. L equals 0 and R equals A. And if int is going to be L plus R minus L whole divided by 2, and this is going to be A plus B plus 1 by 2 minus, okay, it is going to be cut 1. I have made a mistake over here. Are there any other mistakes? And L1, L2, okay, L1 is going to be equal to int min if cut 1 is equal to 0. Otherwise, it is going to be nums1 of cut 1 minus 1. This is fine. Same goes for L2. It is going to be equal to int min if the cut 2 is 0. Otherwise, it is going to be cut 2 minus 1. Okay, this all are fine. L1 is less than equal to R2 and L2 is less than equal to R1. Otherwise, if it goes inside this, we check if the array size is going to be even. In that case, we return max of L1, L2 plus max of R1, R2 whole divided by 2. Or else, if the array size is going to be odd, we return L1, L2's max. Else, if this is false, then we would be seeing if L1 is going to be greater than R2. In that case, we'll be return making R equals cut 1 minus 1. Otherwise, we'll be making L equals cut 1 plus 1. Okay, now let's try. Yeah, now it is running fine. So we have successfully solved a hard problem on lead code, which is asked in many companies even today. So we have solved around 4 to 5 problems varying difficulties, and I hope that you have got a good grip over the concept of binary search, and I'm really sure that you would be able to solve any problem based on binary search now. Yes. So we have come to the end of this session. So after the session, we would be giving you the CP resource sheet where you will be having some practice problems. You can go to lead code or the website where we had the practice problem, and you can check out the same.
So, like, as you guys can see that we have a very less number of people attending our sessions. So you guys can point out or give some feedback to us so that we can improve in the next sessions of further future sessions, so that it'd be better, right?